In this topic, we will be deriving the expression for output current. So this is termed as ideal IV characteristics or long channel IV characteristics or Shockley model. So we will be deriving the expression for output current in all these three regions of operation. So initially, we already know in cutoff region, we don't have enough supply input voltage to make the inversion happening beneath the silicon dioxide layer. So there won't be any channel. So if channel is not there, there is no conduction. So ID is equal to 0. So yes. So in the second case and third case, if a current want to flow, there should be some rate of change of charge. Actually, based on the equation I equal to Q by T, current is based on rate of change of charge. Here, charge is present in the channel based on the inversion. So as inversion happens, this electrons are accumulated near the silicon dioxide layer. So these are all the sufficient charges which is needed to make the current conduction. So if you see the structure, so here gate is acting as a metal, silicon dioxide is acting as a dielectric or insulator, and your channel is again acting as a metal. So in between two metal, we are connecting an insulator. It will act as a capacitance effect. So charge stored in a capacitor can be expressed as Q equal to CV. Here, the capacitance due to this formation of this gate silicon dioxide layer and the channel is Cg, that is termed as gate capacitance, and the voltage that is here they are mentioned as Q channel equals Cg into VGC minus VT is the voltage which is required to make the electron to attract near the silicon dioxide layer. Why VGC minus VT is actually VGC is the required voltage to attract the electron, that is voltage potential difference between gate and channel. But in order to attract the electron near silicon dioxide layer, initially it has to overcome the threshold voltage. So initially whatever input we are applying, after crossing the threshold voltage only, we can able to attract the electron, because after the threshold voltage only the inversion is happening. So we have to subtract that threshold voltage from VGC. That's why VGC minus VT. So Q channel equal to Cg into VGC minus VT. So this is the expression for Q channel, and we have to calculate the expression for time also. So if you see, already we have seen this equation, right? So VGC is the average voltage between gate source region as well as gate drain region. So average voltage VGS plus VGD by 2. So we already have the expression for VGD from here. VGD equal to VGS minus VDS. If you rearrange this equation, that you can substitute here, and you can obtain the expression as VGC equal to VGS minus VDS by 2. That we can substitute here. So that will become Q channel equal to Cg into VGS minus VDS by 2 minus VT. And we have to find out the expression for Cg, that is the gate capacitance. The equation for gate capacitance or capacitance normally is epsilon A by D. So here epsilon is the relative permittivity of the gate oxide, that is equal to the constant into relative permittivity of the air free space. That is epsilon naught x, the relative permittivity of the oxide layer, and epsilon A by D. A is the area, so width of the transistor as well as length of the transistor, W into L, divided by distance between these two parallel plates, that is the silicon dioxide layer thickness, that is T naught x. So it is C naught epsilon naught x divided by T naught x is mentioned as C naught x. So Cg equal to C naught x into WL. So that also we can substitute here. So Q channel equal to C naught x WL into VGS minus VDS by 2 minus VT. So we can modify the equation like that. And now we have to find out the expression for time because I equal to Q by T. We have already find the expression for charge. Now we have to find out the expression for time. So time, what they have mentioned is the time taken to travel an electron from this source to drain. That only we have to find out. So in order to find the time, we need distance as well as velocity because speed equal to distance by time. So if you want to find out time, we have to divide distance divided by velocity. Velocity is v, that is with respect to mobility of the electron as well as the electric field applied between this source and drain. So velocity will become mobility into electric field. Here the electric field is the lateral electric field due to the application of potential difference VDS. That is the potential difference between the drain and source. So E will become VDS divided by L. That is the lateral electric field. So E equal to VDS by L. So that also you can substitute. Time equal to L divided by L is the distance traveled by the electron. L divided by velocity. And you can rearrange the equation. You will get the equation like this: beta into VGS minus VT minus VDS by 2 into VDS. Here what they have done is they are replacing VGS minus VT by VGT. So that's why the equation is modified like this. If you wish, you can substitute this, otherwise not required. So beta into VGS minus VT minus VDS by 2 into VDS. So this is the expression for output current in linear region. From this expression, you can clearly understood that if you see VGS is constant for that particular region. We are not increasing the VGS after that, and the VT is constant with respect to manufacturer, and so VGT will become constant. So beta is already a constant. Mu C naught x WL is also a constant, but you see VDS is varying with respect to VDS value. Sorry, electric field is varying with respect to VDS value. So as VDS increases, this IDS also will increase. So it is a linear relation between IDS and VDS. So that's why this region is termed as linear region. So IDS will increase linearly with respect to VDS only. So next region is saturation region. We have already seen the expression that VDS greater than VGS minus VT is the second expression for second condition for saturation region. But for approximation, we are assuming that in saturation region, VDS is approximately equal to VGS minus VT. That we are substituting here, and we are simplifying the expression as beta into VGS minus VGT is VGS minus VT the whole square. So in saturation region, IDS will be equal to beta by 2 into VGS minus VT the whole square. VGS is a constant, VT is a constant, beta is again a constant. So in saturation region, a constant current is flowing between source and drain. That's why we are mentioning as even though we are increasing VDS, it has no effect on IDS. So IDS is got saturated. Again, it won't rise or fall in saturation region. That's why the name saturation or non-linear region. So if you see the characteristics curve, this is the characteristics curve for nMOS. As we have discussed, initially we are making that VGS and VGD equal to both are equal at that time based on this formula. VGS and VGD we are making equal, right? So at that time VDS will become 0. So when VDS equal to 0, there won't be any sufficient electric field between drain and source, even though you have a proper channel. So there won't be any conduction. So VDS equal to 0 at that time, IDS also 0. So as VDS increases, as we have specified in the linear region equation, IDS also increases linearly based on the different conditions of VGS. And when we increase VDS after a certain level also. Here there is no drastic change happening in IDS. This is the saturation region. You are getting a constant current for different cases of VGS. So this is the explanation for IV characteristics in ideal case. The same I will explain for pMOS also, because if you see in one university question paper, you might have gone through your IAT one question paper also, that they have specified the question like this. In nMOS, the current is flowing from drain to source, but in that question paper, they have specified as uh, explain the different current equations for the case when current flowing from source to drain, like that was the question was framed. So they are specifying about pMOS. So if you compare nMOS and pMOS, all the voltage levels are negative in the case of pMOS. All the voltage levels and current also flowing in the reverse direction. So negative current will be flowing in the case of pMOS. So while explaining about pMOS, I will tell what are all the changes to be done. Consider this is pMOS. So your n-type body will be here. This is P plus. This is also P plus. So while mentioning about cutoff region, VGS should be 5 volt, not 0. We will be applying maximum volt. So VGS will be 5. At that time, IDS will be equal to 0. That will be in cutoff region. And voltage condition also all will be ulta. Here VGS should be less than VTP. Actually, you have to specify the suffix also. Actually, you have to mention as modulo minus VTP. This is only you have to specify instead of VTN. This threshold voltage, every wherever you are seeing this threshold voltage, that has to be replaced with the modulo minus VTP. We will be taking only the magnitude value of the threshold voltage in case of pMOS. So that should be VGS less than modulo minus VTP. This condition is same. VDS also equal to 0. All the voltage level you can mention suffix VGDP, VGSP, VDSP, like that. So in the second case also VGS less than modulo VTP, and this has to be reversed. VGS less than VGD less than VTP. Here 0 greater than VDS greater than VGS minus VTP. So in nMOS, the first case and for linear region as well as saturation region, VGS greater than VT, right? For pMOS, for linear region and saturation region, first condition was VGSN less than modulo minus VTP, both the cases. And second condition in linear region for pMOS, that is VDS greater than VGS minus modulo VTP. Likewise, for saturation region, VDSN less than VGSN minus modulo VTP. That has to be corrected. And for output current equation, IDS equal to 0 in cutoff region, and in saturation region it will become, sorry, linear region it will become minus beta into that you can mention as VGT itself. VDS has to mention as minus VDS, so it will become plus VDS by 2. This minus only coming here. Here instead of VDS you will be putting minus, right? That will be coming here. So minus beta into VGS minus modulo VTP plus VDS by 2 into VDS. So in saturation region, the equation will become beta by 2 into VGS minus modulo minus VTP the whole square. So if you see the characteristics are, so initially when minus VDS or VDS equal to 0, IDS equal to 0, as VDS decreases, here actually we are specifying VDS increases, here VDS, as VDS decreases, output current start decreasing. or output current start flowing in the reverse direction. That is the actual explanation. As VDS decreases, output current start flowing in the reverse direction. As reverse direction current is increasing as per nMOS. Actually, we may not mention it as reverse current in pMOS. Actually, pMOS, the current will be flowing from source to drain in the ulta direction. So we have to specify only as VDS decreases, output current increases in pMOS in linearly, as well as in saturation region it gets saturated. While specifying nMOS and pMOS, while designing a CMOS, the conductivity of the nMOS is high as and the pMOS is low, because in nMOS the conductivity is due to electrons. So electron will be having the highest conductivity. PMOS, nMOS will be having the highest conductivity as the majority charge carriers are electron. PMOS will be having the less conductivity. So while combining these two, we have to choose the size of the PMOS twicer than nMOS, because if we choose PMOS size is twicer than nMOS, so you will be having more holes or more positive charges there. So we can able to balance the conductivity between nMOS and pMOS.